We are now recording. Let me get the slideshow set up. And here we go. Now, we are almost through, and maybe you can help turn on the projector. Okay. Almost through with chapter 12. Now, I hate to tell you this because I'm sure you're going to be awfully upset with me. I don't have your test made out yet. I've got the questions selected, but I just have not had time to sit down and type out the ones I need to type out. So a few of them are done, but there's still some that are not. So I hope to work on that possibly this afternoon. I know I've got several other things to do too, but if I can get those done, I'll hopefully be working on this afternoon as well. Okay, so I don't have it with you ready for today, even though we'll probably finish the section today, finish the chapter today. Any questions on anything we've done so far? Remember, we did the first two sections of chapter 11. We did some other things in that for review type stuff, and then basically the first 6 sections in chapter 12. So that's going to be what your test is going to cover. That's, I believe it's that's 8 sections, so there'll be 2 sections, 2 questions on 2 of the sections, and 1 question on each of the others. Yeah. So probably 11. Those 2 and 11 will be 1 question each, and more than likely 1 question each, and 12:1 through 12:4, and then 2 questions each in 12:5 and 12:6. I'm guessing that's how it is going to be. I can't remember. I don't have it in front of me, but I believe it's something like that. Okay, any questions from what we covered so far? Sorry I'm so late getting you the first test, but had a lot of sort of catching up to do. But all this is going to be useful in what we do later, I hope you'll find. All right, we covered ellipsoids, hyperboloids, and now we're doing paraboloids. Now, if you remember back when we first started our geometric shapes, when you have 2 squares, same coefficients, plus sign in between, that's usually a circle on the plane. 3-dimensional, it's a sphere. 2 variables on the plane, both squared with a plus sign in between, but different coefficients. You have an ellipse. That circle gets flattened. One axis gets elongated, the other gets shortened. Okay? And so, therefore, in 3 dimensions, 3 squared terms, all combined with pluses, equal 1 at the end. That's an ellipsoid. Ellipses in every, this is what it calls them, levels surfaces. Okay, every time you chop them, you get an ellipse any way you chop. The hyperboloids, okay, square terms for all. Hyperbola, let me go back to hyperbola in 2 dimensions. Square terms in both things, but a minus sign in between. Now they're going like this, or like this, or that. Something like that. Okay, those are hyperboloids. Okay, 3-dimension hyperboloids. 2 different types of those. How are the hyperboloids split up? 2 different types.
There are 2 sheets. And
2 sheets and 1 sheet. The 2 sheets is when that equals to a -1. 1 sheet is equals to a +1. Okay, that's how I like to remember. Remember also, 2 of the terms, you have square terms. 2 are plus, 1's a minus. They put it on the other side. I like to put it on this side of minus. And then a +1 over here is a hyperboloid of 1 sheet. If it's a minus sign over there, 2 pluses, 1 minus, and a minus sign, that's a hyperboloid of 2 sheets. And then there was one more that we hit very quickly last time, an elliptic cone. Now, what is that like? basically like that hyperboloid of one sheet that you tighten the belt on until it goes away, and then forms an elliptic cone. All right, now we get to our paraboloids. Tell me how a parabola looks. What's the basic form for a parabola? Okay, I know it looks like this. Okay, what's the equation form for it? Y is equal to x squared. Okay, so a paraboloid will have one variable. This one happens to be listed as z, is equal to either a sum or a difference of the other two squares. The sum, as you might expect, that would be the equation, if this was a constant here, that would be the equation of an ellipse, both squared with a plus in between. This would be an equation of if that were a constant, hyperbola. Okay, so this would be elliptic hyperboloid, paraboloid, and a hyperbolic paraboloid. Okay, one variable's to the first power, the other variable's to the second power. All right, now the one variable that's to the first power, that's the axis. This would be a z-axis. This one would be a z-axis with ellipses going around this way. Actually, if that let's see, if it was a minus z, then the ellipses would be going down. Okay, the hyperboloid would be jumping out. Elliptic hyperboloid. The hyperbolic hyperboloid, oh boy, these are a little different, okay? What you have in either direction, what I mean by that, well, first, when z's are constant, we've already determined those are going to be hyperbole, okay? So slicing your level curves parallel to the z-axis, that'll give you hyperboloids. Hyperbolas, okay? Okay. If you do level curves this way, y is equal to 0 or a constant. That gives you parabole, okay? The z-axis, and if this is x-axis this way, your parabola will be like this. If this was a constant, then your parabola will be on the y-axis like this. The x's would be like this. The y's would be like that. Okay, so you get a hyperbola slicing z's. You get parabola either slicing parallel to x and y. Here's what those look like. Well, no, don't get to see what they look like yet. Let's zoom in on this. Yuck. All right. This is basically what I'm saying. I was using the wrong term. I was saying level curves, which is what they are. This is what calls them horizontal traces. Okay? The elliptic hyperbola, your horizontal traces, those are your level curves parallel to the horizontal plane, are all ellipses. Okay? These are not your ellipsoids, these are elliptic paraboloids. Okay. They've got the slides out of order a little bit here. Elliptic paraboloids, that'd be that parabola like this, spun around the z-axis or whatever axis, and so you have a dish that's parabolic. Okay. If you cut horizontal traces, when z being your axis, every one of those is an ellipse going up, okay? If you cut vertical traces, vertical traces, then these are parabolic going upward, always, unless it's a minus, Hyperbolic parabola, again, your horizontal traces would be hyperbolas, but then your vertical traces One way will be an upward parabola, the other way a downward parabola. Okay. Arm waving doesn't do a lot of good to help you see it. Here's what they look like. Okay. Now, this is your elliptic paraboloid. Z is equal to, these are plus in between, so when Z is a constant, that gives you level curves parallel to the XY plane they call the horizontal traces. Every one of these is an ellipse. Okay? If A and B happen to be equal, then they actually are circles, but it's still a paraboloid. Okay? It would be a circular paraboloid on the elliptic. But, you know, a circle is just a special case of an ellipse. Okay? Now, if this is 2, that means the x-axis is your shorter axis, the y-axis is the major axis, minor and major, of those ellipses that you get when z is constant. But when your y's are constant, slices this way, a vertical slice this way, parabola, 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 always. Or when your x's are constant, then you have your parabolae like this, back side, front side. Now your hyperbolic paraboloid, again, your horizontal traces, those are your curves this way, that's your blue lines here, and you see you get a blue line on this curve and a blue line on that curve. If you're coming to y-axis, your blue lines are here or here, but they're always hyperbola either about on whichever axis, x or y. But your vertical traces, if you cut here, then these are parabola, okay? Pointing up this way, and down this way. And for everybody, I've got to take a look at this before I agree with that.
I think the green ones are the ones.
Yeah, the green ones are the ones on the x. That's it. You're right. Green ones are the ones on the x-axis. No, that's still not right though. They've got this twisted, I think, 90 degrees, because that is a hyperbola that should be going. I mean, a parabola that's no, this is right. It's sort of right. When z is positive, these are okay. Now, I'm not buying this. I think they've got this twisted, because this one would be a hyperbola about the z-axis, and this would be an upward curve. So twist this thing 90 degrees that way. I think it's right then. Your purples would then be opening upward, and the greens are opening downward, which would be that situation. Pretty sure that's the case. I think they've got this picture just a little off. They have it in the new edition as too. So I can't swear to it, but it looks like to me they've got that 90 degrees twisted. Okay, but that's what they look like. Sometimes these are called salad-shaped curves. Okay, if you think about it, the horse goes under this part, and your legs go across that part. You know, it's a salad. Okay, so sometimes these are called, and in fact, we'll later get to it. You find saddle points in those, because it's sort of shaped like a saddle. Okay. Now, here's another hyperbola. This is one that they do have some of those cross curves. And remember at the very beginning, and by the way, I've just been talking about it. These are referring to to exercise examples. We should have had those. So we'll go back and get those. This hyperbolic paraboloid is defined by z is equal to 4xy, or change your axes, twist the axes, and z is equal to u squared minus v squared, where this is the u, and that's the v.
I think that's the first one that has an example with it.
Well, I was thinking those that had numbers with it were examples too, but maybe not. Nope. That was hyperboloid of 2 sheets. That was example 3. Yeah, you're right. Yeah. I think maybe in the old book they had examples, those other 2 did. But boy, we said at the beginning we're not going to have any of these cross terms, and now they're having them. But they're showing us how you can change your variables to align with the u-axis and the v-axis. And when you do that, you get something like this. But that's a ooh, wah, look at this type thing. Now, there's one other type of curve. Okay. By the way, what they left off here, show that z is equal to xy is a hyperbolic paraboloid by writing the equation in terms of the new variables. They didn't tell you what they were. Here's what they were. Of course, when I go to do this, it's going to disappear. Okay, or shrink anyway. Here are the new variables. U is equal to x plus y, and v is equal to x minus y, if I'm not mistaken. Yeah, that's it, x minus y. Okay, now you might say, how does that yield this? Well, if you solve this for x, which you could do by adding these 2 together, right? You add those 2 equations together, what does that give you? 2x is equal to u plus v, right? So x is equal to u plus v over 2. And then y, by subtracting those 2 equations, you get u minus v is equal to 2y divided by 2, and you get y is equal to u minus v over 2. Well, now plug in what we had before. Z is equal to x, which is u plus v over 2, times, okay, sorry, I had a 4 in front of that, 4x, y is u minus v over 2. The 4 cancels the 2 2's out, and that gives you z is equal to u squared minus v squared, which is what this other representation is like. But don't worry about this. You don't need to do it. There, they told you what those parameters were. A lot of times you got to figure out what they are. We're not going to do that, so don't get bent out of shape. But it just shows you how you can make some adjustments and change your coordinates and get it back into more of a standard form. Now, can you do that in every circumstance? Probably not. But all the ones you're going to be running into right away in this text, we're just going to stick with the standard. Now, example 5 says, without referring back to the formulas, use traces to determine and graph the quadratic surface given by, and if I were to go to the slide, it's going to give it away. So I'm going to do it on this slide. So what we're going to do here, this is example 5, has nothing to do with this picture here. But here's what your quadratic, the equation is. X squared plus 2z squared minus y squared is equal to 0. Okay? Now, that's not quite our standard form. Standard form, what we want is the numerators all to be coefficients of 1. So divide by 2. and divide that side by 2 if you wish to. So this would give you x over root 2 squared plus z over 1 squared minus y over root 2 squared is equal to 0. Now that's closer to the final, to the standard form. I'm not sure it was exactly the standard form, but to me that's the one I would use. Now, how do we determine, as it says here, determine what your, without referring back to the formulas, use traces to determine and graph the quadratic surface given by that. All right. So here's what I would do first. Okay. And frankly, the original form to me is good enough. I don't care for those root 2's and the denominators. So if we go back to this first one, what I would first say is, let's just imagine the y was constant. So these are going to be vertical traces, but constant values on the y-axis. What would that give you? Constant value on the y-axis basically is going to give you x equals 0, z equals 0. That's the only way you can get that. If this is a constant, that's 0, these are squares, guess what, folks? There's no way that's going to be except x equals 0, z equals 0, and that would be equal to y is equal to 0. Y is anything, wait, I'm sorry. Move the y squared to the other side, sorry. That is the better way to look at it here. X squared plus 2z squared is equal to y squared. Yeah. Look at it that way. And when y is a constant now, what does that form? Well, this is always positive. So 0, 0, 0 is certainly on there, but what else is? Those are constants. What would that shape be? X squared plus x squared over something, x over something squared plus what? Ellipse. No, that would be an ellipse. Okay, so you got that right. When y is equal to a constant, you have ellipses this way. And they're getting bigger because the bigger y is, the bigger those ellipses are. When x and z is 0, y is 0 too, so it meets at a point, and then going on negatives, they're getting bigger and bigger. That's almost enough to give it away, right? That would be 0, 0, 0 is on it. Cone, exactly. And which is your axis? The y is now the axis. That's it, exactly, because you have ellipses. You have 0, 0, 0. It comes to a point there, and then the ellipses get bigger and bigger and bigger this way, bigger and bigger that way. Now, what you can also do is move this around. X squared minus y squared is equal to negative 2z squared. Okay. Now that's going to be problematic. Well, no, not really too bad. The only way this is going to work is for y to be greater than x, right? Because there's no way this is going to be negative unless y wins here, right? Y's got to be greater than x, okay? And if that's the case, you get hyperbole, okay? If the y is greater than x, then you get hyperbole like this, like this, like this. So that would be, and that, by the way, would be a horizontal trace. Those would be hyperboles going up or down. But the Y's always got to be bigger, okay? So that's why they're like this, okay? Nothing like this. X can't be larger than Y. Nothing is here on the x-axis, not the y. Okay, flip them the other way, and that would be 2z squared minus y squared is equal to negative x squared. And again, here, your this is the vertical trace here along the x-axis, but again, you get the hyperbole like this. Got to, because I probably did it in the wrong direction. Y squared has to win again, so they would be like this. These are vertical traces. So, let's see if that fits our intuition here. They don't show this anymore, do they? Let's see if it's the next one. No, they don't show it. Sorry about that. That would be the two cones, okay. It would be like this, only twist this around like this, okay? So the cones are going along the y-axis. And you see here your hyperbole here, and your hyperbole there. But flip it over so the axis is the y-axis, and you have hyperbole on the x and the other traces. So, man, I probably should have done that to begin with. Okay. Ellipses, this way, only now a vertical trace, one vertical trace would be ellipses centered on the y-axis, coming to a point. 0, 0, 0 is on this equation. An ellipsoid, it will not be on a hyperboloid of one sheet. Hyperboloid of one sheet and two sheets. The origin is not on either one of them. Okay. Now your paraboloids, yeah, they will cross through the origin, but the ellipsoids and the hyperboloids will not. The cones will, and the hyperboloids will. Paraboloids will. Okay. That was example 5 in our text. In the old book, it must not have shown up at all. All right, then one other shape, not quite the same as what we're used to, and probably not the same as what you do. If I said, describe for me a cylinder, what would you picture? Exactly, a tin can, right? A cylinder technically is not. That is a right circular cylinder, meaning its cross-section of its base, usually horizontal trace, would be a circle. Then that's your tin can, if you chop it off top and bottom. Well, technically what a cylinder is, give me any curve in the world, any curve, and then extend that, say, infinitely on the z-axis, or if the curve is on the z-plane, extend that along the y-axis, or if it's on the y-z-plane, extend that along the x-axis. That gives you a cylinder. Cylinders don't have to be closed. You could have an elliptical cylinder just like you have a circular cylinder, okay? Or you could have just any old curve extending. If it's a curve in the xy plane, it extends infinitely in the z, and rotate that all around, and you've got your cylinder. So that's a cylinder. Any old curve, usually along a plane, of course on a plane, but usually one of the coordinate planes, and then extend it. If it's on the plane made by two of the axes, extend the other axis, you go infinite in those directions. So that's the definition of a cylinder. And they call it a quadratic cylinder. I don't think that qualifies as a quadratic cylinder, but it says further examples of quadratic surfaces are the quadratic cylinder. We use the term cylinder in the following sense. Given a curve C, the one they've drawn here is not a quadratic curve. In the xy plane, the cylinder with base of that curve C, the surface consisting of all vertical lines passing through any part of that C, shown in that figure right there. Equations of cylinders involve just two variables, x and y. X squared plus y squared equal r squared. That would be your right circular cylinder, okay, where r is some constant. Okay, and then this next figure shows several of these cylinders. Now, these are all quadratic cylinder. That one we had before, there's no way you could call that quadratic. It's a curve, and it could be a quadric surface, but it's not quadratic, okay? In fact, I'm not even sure it would qualify as a quadric surface, okay? Again, here's your right circular cylinder. This has a circular base in the xy plane, goes infinitely in the z. Not a tin can because it has no top or bottom, but if you did truncate it somewhere, it would be a tin can or a toilet tissue roll, or or anything like that. Okay, elliptic cylinder, your horizontal trace is an ellipse, not a circle. Okay, in other words, A and B are different values. In this case, the A is the larger, B is the smaller, because X is the longer X, major axis, Y is the minor axis. Hyperbolic cylinder, still. Notice these are all quadratic expressions. That's why they are technically your quadric surfaces. Okay. Tony, right? Yes, sir. Hard to see. Well, let's see. I think I already have you here. Who did I? Oh, I marked Ashley wrong. Sorry about that. You're now here. Okay. Okay. All right. Good crowd today. And there would be your hyperbolic cylinder. Draw your hyperbola in the xy plane. There it is. The blue lines there and there. And send it infinitely in the z direction. Hyperbolic cylinder. Okay.
There's one more.
Oh yeah, there's one more. And this is your parabolic cylinder. Draw a parabola in the xy plane. This is with y as the line of symmetry. It's not really an axis, really, but it's a line of symmetry. And then your let z go infinitely positive or negative. That would be a parabolic cylinder. So that first curve was a cylinder, but it was a quadric cylinder. Okay, the one waviness to it. All right, now we have a few that are going to show them again, and we're going to start up here. All right. What is that? Ellipsoid. Notice what you've got here. Every variable is squared. Good. Plus signs in between equal 1. All your constants are divided on the bottom. And the end point here coming out the x-axis is sort of hard to. Oh, there it is right there. That would be the point plus square root of a, and the one back there where exit is minus the square root of a. Okay? The y, this is plus square root of b here, minus square root of b where the left is on the back side, plus square root of c here, minus square root of c there, wherever it exits there. Okay. Important thing to remember, every level surface, every trace, horizontal trace, vertical trace, everything's an ellipse. Except that's a constant, that's a constant, that's a constant. You still get ellipses everywhere. Okay? Hyperboloid of one sheet. Okay? Your vertical, okay. Notice how it looks. Each variable, two variables, all three variables are squared. Okay? Hyperboloid. Okay? But one of them, if you put it on the same side, would be a minus, the other two would be plus in between, okay? Also equal to positive 1, okay? With that being the case, if that's the one that's negative is your z, then your horizontal traces are all going to be ellipses. Just set these as constant, and that just increases that number. Then these are ellipses, bigger or smaller. Smallest at the or on the xy plane, bigger up top, bigger at bottom, all one sheet. Okay? But if you set the y's equal to a constant, then you have x squared minus z squared is equal to some constant. Okay? You have, that forms, y is a constant, that forms your hyperbole this way. There's one, there's one. But when you get to, this is y is equal to a constant, when z cannot be greater than x, okay? If it were, then that was going to be a negative number there. So when it's equal to, z is equal to x, then you're just going to have cross lines there. So it'll be x squared minus c squared. Let's see. Phrase it this way. When y is equal to b, then you have a 1 here, 1 there, and then you get two cross lines this week. X squared minus c squared with the constants involved there. That's going to be factors x plus something times x minus something. That's going to be two straight lines across. Here are the green ones when x is equal to a. That's as far out as you can come here, and then you're going to have two crosses. Hyperbole above and below that. And we've already described it. Okay. Hyperboloid of two sheets looks just like this one except for a minus 1 here. And that minus 1 really limits you because here's one reason. X, y, and z can never all be 0. In fact, x and y's can be 0, then z's are equal to plus or minus c's, okay? Because you multiply through by that. If these were 0, pull the 1 over here, and z would either plus c minus c, okay? And so you'll never have a 0, 0, 0 on that. You won't on this either, but you can have, the x's and y's. Z can never, ever, ever be 0 because x squared plus y squared is always going to be positive, can't equal a negative 1. So that's why there's a gap in the middle. X can't be 0. Z can't be 0 and have any values for x and y. That's what makes it two sheets. But again, your horizontal traces are all ellipses, different values. Any value that z can be, from plus c up and minus c down, this is going to give you ellipses, okay, top and bottom. Can't have any in between when c is between plus c and minus c. No, none at all. Okay. When you do vertical traces for y is equal to 0, you have hyperboles, fuchsia hyperboles here. Make sure hard to see this way. And when x's are constants, then you have hyperbole green like this. It's really close together. You can see them going back this way. You can't see them behind there. You can see these on the front side. You can't see these on the front side. They just make them too hard to see. Okay, so there's your hyperboloids, 1 sheet, 2 sheet, ellipsoid. All right, ooh, that worked out really nicely, didn't it? Your paraboloid, two types of paraboloids, elliptic, in other words, when z is a constant, of course z can never be negative. If z is 0, x and y both have to be 0, so the origin is on that. But then if z is any positive number, your horizontal traces are going to be ellipses. That's an equation of ellipse, if z is positive. That's why the blue curves are all that. Now, if change and make this variable x, then the ellipses will be this way. And make it y, then the ellipses is that way. The single will be linear if it's just linear to the first power. Okay. But if y is constant, then you have x as a function of z. Z is a function of x. And when y constant, then you have your fuchsia-looking parabola this way or back this way, either one. When x is a constant, you have them, the green ones, like this. All curving up as long as z is positive. Yeah. The elliptic paraboloid, your horizontal traces are all ellipses. The hyperbolic paraboloid, oh, and all the other traces are parabolas. The hyperbolic paraboloid, your horizontal traces are the blue ones here, and it's hard to see this the way they've drawn it here, but for every one you've got over there, you got one this way too. This is above the axis, and like this, the traces going down, now they curve around the y-axis. Okay. X-axis that way, y-axis this way. Your vertical traces, though, just like they are here, are parabolas. And I swear, I think they've got this backwards. X is a constant. That would be coming out this way. No, that's right. X is a constant. These are on the YZ plane. These are opening downward. Okay. Is that how they had it before?
Yeah.
Okay, I said it wrong. When X's are constants, okay, these are then down. The traces are this way. Those are the green ones. Okay, and going back that way too. And when Y's are constant, then they're concave up. And those are the purple ones, or the magenta, or whatever color that is, going upward. The horizontal traces, though, are hyperbolas. Everything else is a parabola. Your elliptic cone, now these could be circular. That's a special case of ellipse. That would be your A and your B are equal. Now, they don't set it equal to 0, okay? I would, because to me it's easier to see that way. But obviously, if z is 0, x and y both have to be zeros, okay? And vice versa. If x is 0, no, that's not necessarily true. Then x is, that would be anywhere along axis, x would be 0, and those would then form ellipses, okay? But if z is equal to 0, these two have to be 0. Y is equal to 0, again you get, no, I said it wrong. You get hyperbole, okay? Yeah. Here's the bottom, there's the top. Hyperbole that way, and hyperbole this way. So it's an elliptic cone, but cone because 0 is the origin is there. Okay. Are there any more? Yes, your cylinders. Okay. See if I can pull it. What's that?
Those are the same ones we looked at earlier.
I know. They just did them again in the summary, but they did them a little bit smaller, I guess. Okay. This is your elliptic cylinder. What they didn't show is a circular cylinder. Elliptic cylinder, hyperbolic cylinder, parabolic cylinder. You just, whatever your axis is, goes infinitely up and down, tracing out the curve on the XY plane. All right, I think that's the last one now. Let's see. Yes, it is. All right, homework. Well, let's see. You want to do these 12.6 preliminary questions. Okay, these are kind of straightforward, I guess. All traces of an ellipsoid are ellipses. True or false? True. Every trace. Well, horizontal, vertical. Okay. Number 2. All traces of hyperboloid are hyperbolas. No, you have 2 different types of hyperboloids, right? It's the, yeah, your hyperboloids are your 1 sheet and 2 sheets, okay? And it's your horizontal traces are still ellipses on those, okay? The others, your vertical traces, if it said all vertical traces, you'd have to identify your axis, okay? Number 3, which quadric surfaces have both hyperbolas and parabolas of trace as traces? Well, just take the names from it. Hyperbolic paraboloid, right? Okay, that certainly does. And yeah, I believe that's the only one that does. Okay. Is there any oh, we should be checking the answers in the back just to make sure they got them right too. 12.6 preliminary. Number 1 true. Number 2 is false. They said true mostly for number 1. All traces of ellipsoids are ellipses. They said except at the tips. X equal plus or minus a. It's a point, 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 which is a very small ellipse. Okay. Number 2 is false, period. Number 3 is hyperbolic paraboloid. Is there any quadric surface? All the traces are parabolas? No. What did you say? We hadn't done that yet. Sorry, I gave it away.
Yes.
Yeah, there's none. Okay. Number 5, a surface is called bounded. Now here in the exercise they give you a definition that they have in the text. If there exists some capital letter M that's greater than 0 such that every point on the surface lies at a distance of at most M from the origin, which of the quadric surfaces are bounded? Ellipsoid would just about be it. Sphere is a special case of that because guess what? Everything else goes infinite. So better be ellipsoid. Sure enough it was. And number 6, what is the definition of a parabolic cylinder? Definition. Yeah, it would be that one. It would be a shape that forms a parabola in some plane and then infinitely large perpendicular to that plane, positive or negative. So they say all vertical lines passing through a parabola C in an XY plane, that would be a parabola. Parabolic cylinder. Okay, homework exercise. Please try to do these. They are not particularly easy, especially if you have to draw them, but see if you can pick them up from their equations. Any of the odds 1 through 5, any of the odds 7 through 11, either 13 or 15, no, any of the odds 13 through 17, no, through 19, okay? And then, these are sort of fun to do. 21, okay? Try to do 23. 21 is sort of fun. And I think 23 will be fun too. But, and then do any of the odds 25 through 37. And then any of the odds 39. Oh, I see. 39 or 41. Actually, should be able to do all 4 of those, but only the answers for the 39 and 41 are in the back. and then either 43 or 45. Now, there's a further insight and challenge that also says a hyperboloid of one sheet is called a doubly ruled surface. In other words, let's see, well, you can read that. You don't have to do those, but I just thought you might find that one sort of interesting. And any of the others you can do. All right, now, do you think that most of your majors you're going to run into spherical and cylindrical coordinates? I don't want to do too much on this. Yeah. If you've taken physics, you probably already run into, I just saw something here. You probably already hit them some there. Where did I see? I thought I saw something about, yeah, magnetic fields. You're basically doing some stuff in 3 dimensions when you're dealing with electromagnetic fields. They have to be because they follow cross products. So if you'd like a slideshow of it, we could do it, but I guess I ought to just so you can at least have seen these. You're not responsible for these on the test. So actually that was a good slide to do. Okay. So let me get out of here because this is something that you will run into probably somewhere, okay, if you haven't already. So let me just give you the quick and dirty on this. Just going to be the slideshow. If it'll ever open. It doesn't seem to be opening, it's just quivering. It does this every now and then. I don't know what. Ah, here it comes. There we go. And do they have 12.7 in the old text? They do, okay. I thought they did, but I couldn't remember that for sure. Okay. Here it's done this before. It acts like it's open, but it doesn't show. Try it again. Okay, I'm going to close that and try it again. Now it's acting like it's doing better. Yeah, okay. So slideshow from current slide, and we'll blow this up. Let's see. That's not it. This is the one I want. Okay. Now, XYZ coordinates are often called rectangular. It makes sense to call it rectangular coordinates when you're talking on the plane, okay? But in space, it should be a rectilinear equation or parallelepiped or something like that. But we call them rectangular coordinates. Some shapes just fit cylindrical coordinates so much better. That example of magnetic field around a wire, that fits a cylindrical coordinate far better than it would rectilinear coordinates. Okay, and here's what a cylindrical coordinate is. In rectangular space, x, y, z, all perpendicular to each other. In cylindrical coordinates, if you remember back to polar coordinates, your coordinates were r and theta. And r always listed first, theta always listed second. For cylindrical coordinates, you just add the z component. So the x, y don't exist, r, theta do. X's and y's can be expressed in r's in terms of r, theta, and vice versa. And then z is the same as it is in 3 space, in rectilinear coordinates. So now the cylindrical coordinates would be r, theta, z. Okay? On the xy plane, it's just r theta. Okay? 3 space in r theta is z, r x, y is z. They go back and forth. Okay. And anything that has some cylindrical symmetry, this is a system that would be far better to use. Now here are your conversions. Actually, it's easy to do it from here. Going back and forth between cylindrical and rectangular. If you're given cylindrical, it's easy to get rectangular. Remember, x is always r cosine theta. Y is equal to r sine theta. This is just your good old vector thing. Z is equal to z. When you're going rectangular to cylindrical, then remember, your radius is always the square root of x squared plus y squared. This isn't spherical, this is cylindrical. The radius of the cylinder is always the square root of x squared plus y squared. The theta is gotten from the tangent theta is equal to y over x, which means theta would be inverse tangent of y over x. If you're writing the things, I would put it that way. And z is still equal to z. Okay? Pretty easy, pretty straightforward. If you know polar coordinates, you know cylindrical. They're exactly the same with z is equal to z. Okay? Now, this is probably from an example, so we won't go into it too much, but go into it at all. I can't see it well enough to zoom in and see what we got. Oh, I see. Here's a point. I don't know which they gave you. If they gave you the point negative root 2 on x, positive root 2 on y, and positive 5 in z, in cylindrical coordinates, it's pretty obvious if you have negative root 2, positive root 2 as your x and y, that puts you somewhere in the x coordinate being negative, y coordinate positive. That puts you in the second quadrant of the xy plane. So going around this way. So that would be, the theta would be, and they're the same values, so that would be 1/4 pi, 2/4 pi, 3/4 pi. There's your theta. Your r would be the square root of this plus that. That would be 2, okay? Square root of 2 is 2. The square of the square root of 2 is 2. The square of the square root of minus 2 is 2. And the 2 plus 2 is 4. Square root of 4 is 2. So there's your r, and then your z is the same, 5 and 5. Okay. So that's pretty straightforward. We didn't have to use the inverse tangent because you could reason out what your theta was there. Okay? I don't know if this is worth doing too much to. All right. These are some points. Basically, this is a plot of theta is equal to 7/6 pi. That would be the line that goes here. Now, no, I guess they're given a point here. You do, but again, you can get the theta from your inverse tangent of y over x. That's what you would do. Now, assume these are rectilinear coordinates. So y over x, that would be 1 over root 3. Inverse tangent of that would be pi 6. But that would have you in the first quadrant. These are negative, so you have to add pi halves to that. Pi, add pi to that. Pi plus pi 6 would be 7/6 pi. So you get the theta coordinate here. The r coordinate would be the square root of this squared plus that squared. And then your z for this point would be 0 to that point. I'm sure there was something else to the problem, but that's what we're dealing with there. Okay. Here's a classic place where you would use cylindrical coordinates if you're dealing with a cylinder, okay? Now, what are the level surfaces of a cylindrical coordinates? Well, this is one particular shape, which would be, looks like an elliptic cylinder. It could be a circular cylinder. And your z is equal to 0 would be the xy. That would be where it intersects the xy axis. But for any old z is equal to c, you would have this still, your radius is equal to some fixed. So this would be a circular cylinder. R, little r is equal to r, always, and that's it. Every circular horizontal trace would be a circle centered at the z-axis, okay? Or your horizontal traces would then be circles. Your vertical traces would be various values for theta, okay? You don't have x and y's in various thetas. Theta is equal to theta naught, that would be a plane coming out this way. So your surface would be the line that goes down that would be your trace there. Okay. You really don't need these much. I not run into them. Now, what if you had shapes like this? Guess what kind of coordinate system you'd want to use here? What's that a shape of? A sphere. So here you would use spherical coordinates. Now here's the big difference in spherical coordinates. The first is a radius also, but it's not called r. It's called rho. That rho is the radius from the center anywhere, not just in the xy plane, anywhere. That's your rho. Your theta is basically the same as before. Picture your positive x-axis through the center, go around toward your positive y-axis in the xy plane, and your theta is exactly as it was in the cylinder coordinate. Your radius is different though, okay? And then your third coordinate is another angle, not another radius like it was before. It was z before, but now this is phi. That's the distance down from the positive z-axis. So the theta coordinate, just like before, is from the positive x-axis, but staying in the xy plane. The phi coordinate is the angle from the positive z-axis to the line in question. Okay, from the origin to the point in question, that angle there would be your phi. Okay, so your three coordinates are rho, theta, phi. One radius, one linear measure, and two angular measures. Now, as you might expect, these equations of equivalence are quite a bit stranger. But they first are going to show us one of these, so let's do this first. This is any old point in XYZ space. We're going to determine its value in spherical coordinates. If this is your point, P, your some distance x, some distance y, some distance z, there's your P. Okay? Well, your rho is going to be the square root of x squared plus y squared plus z squared. That's going to be that distance there, the radius. So it's similar but not quite the same as your as your polar coordinate square. Okay? Or cylindrical coordinate square. All right. This doesn't have an analogy back to two space. This is strictly a three space thing. Okay? Now, your theta, just like it was before, the tangent of theta is equal to y over x. Nothing has changed there, so the inverse tangent is equal to the inverse tangent of y over x is equal to your theta. That's how you're going to get that. So all you need to know is XY coordinates in the XY plane. That's all you need to get there. So whatever these XYs are, they'll give, no matter what the Z is, they'll give you the thing. Okay, now, your phi though is a little stranger, okay? Because you remember, this is a road distance, okay? And I know that the angle here doesn't make it look so, but this is the hypotenuse of this right triangle. The z-axis, the axis parallel to the xy plane, and this pink line here, that's the right triangle, okay? Now, taking a look at this, of course, that hypotenuse is rho. The line here that's parallel to the xy plane, all right, that is what we would have called the radius in polar coordinates or cylindrical coordinates. And that's x squared plus y squared is equal to r squared. Okay? So that's how you get this. But that r is also equal to, this r is equal to rho times the sine of this angle phi. So that's the opposite side, there's your hypotenuse. I know that doesn't look like the long side. That does, but it's not. That's because it's coming out of the board. This is your long side, and it's this over. Okay. So therefore, your r is equal to sine rho sine phi. This r is not a spherical or a rectilinear coordinate. It's a polar or a cylindrical coordinate. Okay. So this is showing some of those relationships. Z is rho times the cosine of theta. There's your rho, cosine of phi. So there's that is. You got your rho, your theta, and your phi. That's what gives you pretty much that. Now, let's look at some comparisons. Yeah. And again, you're not responsible for this course, but if you ever need it, at least you've been exposed to it. Whether you got inoculated with it or not, I don't know, but you've been exposed. Spherical to rectangular. Now, x, remember, is a length. In your spherical coordinate system, rho is your only length, so you got to have a rho in every one of these. Okay, you've got to. The others are angles. Okay? So your x is rho times the cosine of theta times the sine of phi. Okay? Because if you remember, x was r cosine theta, but your r was rho sine phi. So that's where that comes from. Y is rho times is r times the sine of theta, but r is rho times the sine of phi. So you have a sine there. And z, as we saw, was rho cosine phi. Okay, that's going from spherical to rectangular. Here's your spherical, that's the way you get your rectangular. Going the other way isn't too bad. Okay? Rho is the square root of x squared plus y squared plus z squared. We saw that before. That's that distance. Okay? That's your distance formula. The theta, exactly like before, tangent theta is y over x, so theta is equal to inverse tangent of y over x. But then you have to make sure you get it into the right quadrant by adding sometimes pi to it. Cosine of phi, on the other hand, was z over rho. This isn't in, okay, rho, remember, was this thing. So it would be z over the square root of x squared plus y squared plus z squared. Okay, so that's how you get it. And then the phi would be the inverse cosine of z over square root of x squared plus y squared plus z squared. And again, you might have to do some adjustment to get it in the right quadrant. Okay, but don't sweat that too much. You don't have to know that for this course, but if you ever do need to know it, you've at least seen it here. Shouldn't be too hard to go back and reproduce, hopefully. Let's see what we have here. I think this is just an example, but we might be able to get something out of it. Okay. here's a point with spherical coordinates. So 3 stands for?
Theta.
That's the rho. Rho is always the first. That means the radius of phi from the origin to that point P. Pi third stands for?
That one's theta.
Theta, and that's in the xy plane from the positive x-axis rotated around 60 degrees of pi third radians, and that gets you over here. Now this would then be your r, which is not spherical. This would be polar or cylindrical coordinate, and that would get you to that q. And then, so there's your theta. Your phi, on the other hand, is the last one, and that's what comes down from here, which would be the cosine of, the sine of phi would be this r that you have here, and then you can get r. So anyway, that would be pi fourths down here. If all you're given is that coordinate, all you have to do is rho, theta, phi, and that gives you the point. Rho gets you how far out, r gives you how far around from the x-axis, and phi is how far down from the z-axis. Find where those all collide, and that's your point. All right, let's see what this one's doing. Didn't go where I wanted to, but it's fine. Now, this time we have the rectangular coordinates. 2 in x, minus 2 root 3 on y, and up 3 on z. Okay? And they're trying to get you to come up with your polar coordinates. Okay? Easy to get rho, how? Square root of?
Each of those squared.
Yeah, that would be 4 plus 12 plus 9. 4 plus 12 is 16 plus 9 is 25. Square root of that would be 5. So your rho is 5. Okay? I gave you an easy one. Okay? Your theta that you need here, that would be the cosine of theta is equal to y. Tangent of theta is equal to y over x. Okay? And that ratio is minus root 3 over 1, right? Well, what does that give? Minus root 3 over 1. Draw your triangle. Root 3 would be the opposite side, xy plane. And 1 would be this. So this would be the angle that would be up like this. So this is 1, that's 2, and the square root of 3. That's a 60, 90 triangle, with this being the 60, or pi thirds. So, this pi thirds, but pi thirds would have you in the first quadrant. Add pi to that, and no, I'm sorry. This is positive x, but negative y. That puts you in the fourth quadrant. So then that would be a minus pi thirds,
From 2 pi.
which would also be, subtract that from 2 pi, and you get pi thirds. So that's how you get your theta there. By the way, the rho, of course, is always positive. It's usually the case to get theta and z also being positive. I mean, theta and phi. Phi is pretty, I mean, it's got to be positive. You don't go past anything. So that would be that. Now, phi, remember how we did that? It was the sine of phi was this r over rho. Okay? R you get from the square root of x squared plus y squared. Okay? And the sine of that, you know, so once you've gotten the phi, I'm sorry, you're getting the phi, so it's the square root, so you've got that formula to go through. So let's not spend too much time with it, but it is a sort of an awkward thing to do, but it's doable. It's all doable. You got calculators. It's easy to do. All right. I think these are summary type things because we've seen them before. No, maybe not. Let's see. Sphere and spherical coordinates would be rows equal to some value r. That's the sphere at center r. Okay. A vertical half plane would be any place where theta is equal to theta naught. Okay, this is rho's equal to a constant. This is theta equal to some constant, theta naught. That would be a vertical half plane. Okay, and your right circular cone would be described by phi is equal to phi naught. Pick you some angle phi and let that go all the way around for any x, y, any r theta. You get a cone, right circular cone. No, we hadn't seen those before. Okay, now that looks familiar, doesn't it? It's a globe. Okay, the Earth. Okay, pretty much like a sphere. So spherical coordinates. The rho would be the radius of the Earth, anywhere on the Earth, the distance from the center of the Earth. Now, true, the Earth is not a perfect sphere. It's called an oblate spheroid, but on average, it's a perfect sphere. Okay, so there would be your rho. That's the radius of the Earth, and you can look that up in a table anywhere. Your theta would be how far on the xy axis, if you drill in here, xy plane, how far around here. If you pick any line here, well, they've already picked it for you. It's called the Greenwich mean line. In Greenwich, England, is I think they call it the British Naval Observatory. Britain, Queen of the Oceans, you remember, like that, naval power. So their naval observatory, big, powerful place, and there it's just, looks like here it's a little west of London. I was thinking a little east of London. I think it is. I think they've drawn this poorly. But it's going through Greenwich, England, and it's called Greenwich Mean Time, by the way, and everything else. You take your theta either, if you go to the counterclockwise looking down, that's your theta. From how many degrees are you from the Greenwich mean line? They call it the prime meridian. Okay, first that's where you zero latitude. Longitude. They don't list longitude, but zero longitude is Greenwich mean line. Greenwich is this curve here. Okay, from that curve, the angle around there is your longitude. Now, we usually go east this way, west that way, so it goes to positive 180, negative 180, or 180 east, 180 west. We usually refer to that. Latitude, though, we measure it in the angle between the center of the Earth and the equator up, which would be exactly the opposite of feet. Okay? So therefore, the latitude would be 90 degrees minus feet, because from the equator up to the North Pole would be 90 degrees. So latitude, north or south, is 90 minus, the northern hemisphere, 90 minus feet. The southern hemisphere, your phi is a obtuse angle, so it'd be 180 minus feet. So northern latitude. So that's latitude and longitude. They just didn't show you longitude on here, but that's exactly what it is. This angle theta is east longitude. Okay. This looks like almost the same thing, doesn't it? See if there's anything new here. Can't see any. Yeah, Greenwich mean line. Greenwich. Prime meridian that goes through Greenwich, through the North and South Pole, and through Greenwich, England. That's the prime meridian. Theta's to the left or east longitude, to the negative thetas would be west longitude. Latitude, measured from the equator north, which would be phi of 90 minus phi in the northern hemisphere. And it would be 180 minus phi in the southern hemisphere, I think. Okay. I don't think there's anything too new here. Cylindrical to, going back to cylindrical. Rectangular to cylindrical, we've already hit this. I can't think why we're doing it again unless this is in the summary. This is the summary, okay. So you've seen it before. R is the radius of the cylinder from the origin to the point in the XY plane or any horizontal trace, that matches that. So that would be from the positive x-axis around counterclockwise, that's your theta. Your r is square root of x squared plus y squared, and theta, of course, would be the inverse tangent of y over x, and the z is z. Nothing changes with z. And you can go back and forth either way there. X is equal to r cosine theta, y is equal to r sine theta. No, I said it back. No, I said it right. Yeah. Spherical coordinate, again, this is summary. So it's review. For your x, y, z here in rectilinear coordinates, your r, your rho is square root of x squared plus y squared plus z squared. That's your radius from the center to that point. Your theta is the same as it was in polar or cylindrical coordinates from the positive x-axis around the positive xy plane in counterclockwise direction. That's your theta, square root of the inverse tangent of y over x. And then the phi would be the angle from the z-axis to the line from origin to the point. And so therefore, phi would be, the sine of phi would be r over rho. R being r, the square root of x squared plus y squared, or x equal r cosine theta. Then you can work all those around and get them. Wow, they show you this again too. I guess they think it's important, okay? Now this is not quite the same way they did before, but these are given x, y, z, rectilinear coordinates, cylindrical, r is equal to square root of x squared plus y squared, rho is equal to square root of x squared plus y squared, z squared. Theta, same in both, tan theta is y over x. Cylindrical, z is equal to z. The third component is spherical is phi, and that's z over rho. The rho is, the cosine of phi is z over rho, where rho is the square root of x squared plus y squared plus z squared. Okay. Here's one more, going the other way. I can't talk. How do you get from cylindrical or spherical to x, y, and z? X is r cosine theta, y is r sine theta, z is equal to z. You should know those from physics, nowhere else. Spherical, x is equal to, these are the strangles. R cosine phi sine phi, and cosine theta sine phi. That would be x is r cosine theta, but r is equal to rho sine phi, so this would be rho cosine theta sine phi. R again is rho sine phi, so since y is r sine theta, this would be rho sine phi sine theta, whichever order, and z is equal to z, or over here z is equal to rho times cosine phi. I take it it's getting close to that witching hour. Huh?
You got 5 minutes.
5 minutes. We'll be through with this, I think, in 5. I do not have your test ready for you, but I will have it ready on Wednesday. Basically, I picked out the questions and don't have them typed up. This is going the other way. These are your traces, okay? In cylindrical coordinates, your r is equal to some fixed radius, okay? Theta is equal to theta naught, z is equal to some constant here, horizontal plane. So your traces would be r is equal to r would be a cylinder of radius r. Theta is equal to theta prime would be a vertical half plane at that angle theta. Naught, z is equal to c would be a horizontal plane. Those are your traces in the 3 dimensions r, theta, and z for cylindrical coordinates. For your spherical coordinates, it won't be a cylinder of radius r, a sphere of radius r. Rho is equal to r, some fixed value. That would be a rho trace, okay? Theta trace would be vertical half plane, just like it was here. And phi is a constant, that would be your right circular around. That was it. Okay, again, you're not responsible for that for the test, but if you ever need it in the future, you've seen it. Okay? Again, I'll have your test done. Probably one question 11.1, one question 11.2, one question 12.1, one question 12.2, one in 12.3, one from 12.4, 2 from 12. 5 and 2 from 12.6. I'm guessing that's what it is. I may have I know 2 from 12.6. I just can't remember which other one I did it. All right, so let's end that. How much time do we have? We have 3 minutes, right? This is just barely going to be time enough to go back here. All right, chapter 13. Some of these things want 1 click, some of them want 2 clicks. All right. Chapter 13 is talking about calculus of vector-valued functions. Okay? They aren't quite the same figures, but we'll start from this slideshow. We got 3 minutes. Let's just hit the high points for right now. Now, I usually don't see these 2 words together. Maybe I just don't read the right literature, but DNA polymers form helical curves whose spatial orientation influences biochemical properties. I think of DNA as the stuff that's inside every cell, okay? And I don't know why they call it a polymer. I think of that as something synthetic. It probably isn't. But these helical curves, that's what basically something following a circular trace on one axis, but it's moving in Z, say, that forms a helix. And these are helical pairs that tie DNA together. So I guess that's why they call them polymers. Just a little ooh-wah. Okay. Now, what we're going to be talking about in this chapter are vector-valued functions. Okay? We've already hit some of these in earlier chapters. That's why I did that, so this will make this go faster. So R of t, now this is in 3 space. Seems like when we did it before, it was mostly in 2, but there have been some in 3. R of t. R is a vector. That's bold. Okay? That's a vector. Vector components here, so x of t, y of t, z of t. These 3 coordinate functions are functions of that parameter t. X of t, y of t, and z of t. Those are your coordinates for your r of t. The other way you could write that is x of t I plus y of t j plus z of t k. That's how we used to do it. We didn't used to have these angle bracket things. I found these much easier to work with. So that's a vector valued function. Each of its coordinates are functions of some parameter. Okay? Now, how are we doing on time? Is it time? Okay. We'll begin next time with this figure here. Okay? And there's one thing I want to do beyond what this, oh yeah, they have it in there. But we'll begin there next time. Didn't do enough to get any homework exercises there, but from 12.6 you have them. We'll get moving on 13.1 more next time, and I'll have your test ready for chapter 11 and 12 next time. We need to move pretty quickly through this stuff. I should have moved much faster through the last. Good deal. We'll see you Wednesday.